Hey, what's up everyone? Jason Turley here, back with more ROP Emporium. And last episode we checked out Ret to Win, which was the first challenge in the series. And today we'll be looking at Split, which is the second challenge. And then we'll just mosey on and continue the rest of these in another video. So let's click on Split and read the description. So the elements that allowed you to complete Ret to Win are still present. They've just been split apart. Find them and recombine them using a short ROP chain. And then it gives us the option to choose one of four binaries here. And then if we continue to read on, it does tell us that we still have access to the system call, which allows us to execute arbitrary commands or whatever command you pass to it. And the flag bin cat or the string bin cat flag.txt is still present in the binary. We just have to find it. We might have to do a little bit of digging. And then they're confirming that NX is still enabled, or NX, or data execution prevention, however you like to refer to it. Either way, the stack is not marked as executable. You can read to it, or you can read from it, you can write to it, but you can't execute code. And when you can't execute code on the stack, you need to do something called return-oriented programming, or ROP, which is the whole point of this series, this challenge. So if we want, we can continue on and read the rest of this, but let's just get our hands dirty and download the file. I'm going to do the x64 for this tutorial, but feel free to do any of the other ones. So let's wget and download our zip file. Okay, and now let's unzip it. And I'm going to specify tac D. Oops. Didn't know what happened there. I'm going to specify a tac D to specify an output directory, and I'm also named that split. I no longer need this zip file, so let's delete it. Change directory into split, do an ls tac la. We see we have the flag.txt because these set of challenges are a bit different. They give you the flag to start with, and it's up to you to exploit the binary. So if we just run it and see what's going on, it prints out the title, Split by ROP Emporium, tells us that this is the x86-64 version of the binary, and then it's contriving a reason to ask for user data. So let's just type whatever we want. Please subscribe. And it says thank you, and then it exit. So let's run file. Let's actually see what's going on here. So it's an ELF 64-bit executable. It is dynamically linked, meaning that any of the library code, so anything from like libc that it might need, it needs to exist on the system that it's running on. It's not statically linked or statically compiled. It doesn't have any internal libraries that it's using. Every library call or function that it needs to go out and grab it. And you can confirm that with LDD and then split, LDD split. And it actually tells us the libc version or the shared object or the library that it is using. If you're more comfortable with Windows, you might be familiar with .dll files, which are dynamically loaded libraries or dynamically linked libraries, one of the two. So on Linux, you have .so, and then on Windows, you have .dll, but they're essentially the same thing conceptually. And then we can also see that the binary is not stripped, so it does have all the useful debugging symbols. Let's do a robin2 with tac lowercase I to examine some of the imported functions, so things that would exist in the C standard library or libc that this program is using. So put string to print out information to the screen, system to execute commands, printf, memset, probably used to clear out our buffer or zero out our buffer, as we saw in the first episode. A call to read to actually read in our user input. And then we see labels or symbols for main, and then set vbuff, which isn't really too important here. So nothing too juicy. We could note down the address of system. So once we overwrite the return address, we might want to point it here. But let's continue to dig. Let's do tac z to look at some of the strings that exist inside this function. Okay, so we saw this earlier once we ran the program. These are just like the banner that gets printed out, contriving a reason to ask for user input, thank you. And then this is interesting, these last two lines. we see the string bin ls, which is a command. We've used it a lot. Bin ls, or simply just ls, to list what's in your current working directory. And then we see this bin cat flag.txt. And something interesting here, we see that these are in different sections. We see that ls and everything else, the first 6 symbols, the first 6 strings are in the RO data section or the read only data section, whereas bin cat is in the .data section and has a completely different virtual address with 601060. So that's kind of interesting. So we could grab this and take a note of that if we really wanted to, but let's continue on. If we look back at this beginner's guide that's linked with ROP Emporium, we do see some useful commands and tools. And one of them that I don't think I showcased in the last video was TACQS for Robin 2. So if we do TAC_I, like the little I, TAC_I, this lists the imported functions from shared libraries, which we saw, but with TACQS, and then if you filter it out with this grep command, you can list just the functions written by the programmer. So just maybe user-defined programs or functions. So let's grab this. I'm going to slam this into my terminal, and then instead of leaving this as binary in these angle brackets, we're going to put in our binary split. And we do see it prints out some more useful information. We see the call to pwn_me. We see useful function. That's interesting. And then we see something called useful string. So if we wanted to, we could open this program up in GDB at this point. Alternatively, we could do something called object dump, which just to disassemble the program. Let's do TAC_D to disassemble everything, all sections, TAC_M to specify that we want to use Intel syntax, because by default it uses the very ugly AT&T syntax, and this would be a lot of output, so let's pipe it to less and hit enter. Let's actually get rid of this, so now it's a little easier to read. So if I do slash to search and do a .txt to go to the text section, we can see _start. The text section contains all the code. So start is very similar to main. It will call libc start main, as we can see right here, but nothing too interesting, honestly. So let's just search for main. And then we see some calls to put string here that prints out the banner. We see this call to pwn_me. So if we scroll down here and we look at the disassembly output of pwn_me, is there anything interesting? And perhaps I'd actually want to look through this in GDB so I can print out some of these values. But I know just from the last episode, we see this call to read, and right above it, we can see our buffer being allocated with OX 20 bytes. If we want to see how much that is, we can open up Python and do OX 20. Okay, so 32 bytes are being allocated for our buffer, and how many bytes are being allocated. And we can read up to OX 60 bytes. So I do OX 60 in Python, that's 96. So when we run split and it asks for user input and it just hangs and waits, you can enter up to 96 characters, which is a lot. That's more than the buffer can hold. So the buffer, the data has to go somewhere. So it goes past the bounds of the buffer and it will overwrite something called the base pointer and then hopefully the return address. And if you can control the return address, you can control the execution of the program. So let's take note of this. We see this call to useful function, or the disassembly of the useful function. We see it calls system with this address. That's interesting. Let me search for useful string. Is that present in here? Useful string? It is. Not really sure what any of this says. So if If object dump in the disassembly, sometimes it's good to look at, sometimes it's not too helpful, or sometimes you'd like a little bit more context. So after you disassemble a function or a binary, it might be better to open it up in a debugger like GDB, the good new debugger, and that's what we'll be using. So GDB, give it the function, or the binary, I'm sorry, give it the binary you want to analyze, smash enter, and here we go. So you see my prompt says GEF. That's because I'm using an enhanced framework called the GDB enhanced framework that just gives it a bit better syntax highlighting. So let's disassemble that useful function that we saw earlier, and we see it calls system. This value is being passed to EDI, so this is the argument for system. And if we're not familiar with the system command, we can always open up the man page just to confirm it only takes one argument, a pointer, and a pointer is basically the same as a memory address. So it takes the memory address of something, some command to run. So if we go back here and we grab this, since we saw it's a character pointer, we can do examine. So X for examine, /s to specify we're going to give it a string. So slam in the address that you want to examine. We hit enter and we see it calls bin ls. So if we can return execution to useful function, we should be able to get it to run bin ls. So how do we do that? We need to overwrite the return address. From the last episode, we saw that it was 40, but let's just do it again. Let's do pattern create 100 to grab the sequence of 100 characters. Now when we run the program and it asks for user input, we slam this in and we see that it crashes. And the good thing about GEF is that it prints out all this additional context for us. So we can see the status of the registers and with the contents of them. And if we see here, we see our stack. It contains all of our random junk that we sent, beginning with FAAAA. And there is a seg fault. We can see it here, right here. So the program name split, it stopped at this address. The reason is a seg fault. So if we want to actually examine how many bytes it took to overwrite the buffer and the base pointer, you can easily do this with pattern search and then $RSP to point to the stack. And we see that it took exactly 40 bytes to overflow the buffer and the base pointer. So that is awesome. Let's do a disassembly of the useful function one more time, and let's grab this address and let's actually start crafting an exploit. So I like using Python. It's a very, very powerful tool, especially for doing exploits. So let's do user bin env Python. And let's use a module called pwn tools. So from pwn import all, which is just a great way for capture the flag and binary exploitation scripts and exploits. It just has a lot of additional features that make this thing easier. So we need to name our process, or we need to specify the name of the process we are attacking, and that's just going to be split. Let's start crafting our payload. We're just going to send 40 A's. So A times 40. And let's also slam in the return address of useful function. And now let's send that. So p.sendLine payload, p.receive all .decode. And let's actually print this out. Okay, we need to actually define what useful function is. So I'll make a little comment here for addresses. Useful function equals p64 of the address that we grabbed earlier. So far this looks good. We can just say 40 bytes, 32 for the buffer, and then 8 for the base pointer. Anything we're missing? I don't think so. Let's save and exit out of this. Let's do Python exploit. Let's see what happens. Okay, contriving a reason to ask for user data, and then it says thank you. There's no seg fault. So nothing crashed, but it also did not run in ls. If we watched the last episode, the first challenge, this is a very, I'm calling it a quirk, but it's not really a quirk. I guess it's just a feature of doing x64 assembly. You want the stack to be 16-byte aligned. Programming, compilers, CPUs, they usually like doing things that are divisible by 2 because everything is binary, either 1 or 0. So I'm sure there's more reason and math and science behind it, but the stack frame, everything needs to be divisible by 16 when working for x64. And there's a couple ways you can get around this. And this is all documented in the beginner guide if you're not familiar with any of this. So 2 ways we can do this are, instead of using the address of useful function 400742, we could instead jump deeper inside the function, or alternatively, we can grab the address of a ret instruction, RET, return. So let's just grab this, come over here, back to our exploit. Oops, I have caps lock on. Vim exploit. And let's add this instruction. Let's call it ret adder P64. And now let's add this. So now we are printing 40 bytes of junk, and then the return instruction, and then the address of useful function. And if we want to see this a different way, instead of doing P equals process, let's actually, what's going on? There we go. Let's make this gdb.debug, just so we can get a sense of what's going on here. So quit out of this, rerun our exploit, and now it opens up in a separate window entirely, and it goes directly to GDB, and we can see that it has grabbed our process. It says no such file or directory. Remote connection closed. Let's exit out of this. Did I spell something wrong? Okay, I called this ret. I need to call this ret adder. I love Vim, but if you hit like one wrong key, it like freaks out. There we go. So it opened up in GDB and it is paused. So if we want to continue, I don't know if you guys can see this. Let me hide myself real quick. So it's paused. If we want to continue execution, we can just do continue or C. And there we go. So it ran all the way through, but let's actually set a breakpoint. Let's set a breakpoint on the useful function. So I'll just do break useful function. And now let's rerun this program. Okay, fine. Let's continue. Come on. All right, let's kill this. Rerun. Make sure you guys can read it. Break useful function. Actually, where do I want to set my breakpoint? Delete 1. Let's break on pwn me. Continue. So we hit our first breakpoint. It says we're in pwn me. We want to confirm. If we do a disassembly, we see we are in the pwn me function. We're here. So we want to go until we get to this read call. So let me grab this address and just break right there. Hit C to continue. So this is right before the call to read. So our user input has not been sent to the data, our 40 bytes of A's, and then the return instruction, and then the address of useful function. Those have not been sent yet. So we can see here the current contents of the stack are all 0. They're all null. And if we look here at the current instruction pointer, we can see that the call to read is about to happen. So I'm going to hit next I to step 1 instruction. So our user input was sent, and we can see 40 bytes of A's are on the stack. Our base pointer has been overwritten as well. The nice thing about GEF is that it adds these like comments, I guess, these variables that show exactly what's being overwritten. And then underneath our 40 bytes of A's, we see the return instruction that we took from the very bottom of the useful function. And then we also see the starting address of useful function being pushed on the stack right after that. So if I hit NI a few more times, we can see that we're stepping through. We're about to exit this function, so the call to leave is being called. Return. And now you can see here, you can see on the top of the stack, useful function, and you can see the current instruction pointer is set to useful function. If I do a disassembly, just to beat and belabor the point home, we are now inside the useful function function. So NI, we're just stepping through. So we see EDI, it will contain the bin ls. So if we come up here, we see that right now it's blank, it's 0. If I hit NI one more time to step a single instruction, now I scroll up, we see RDI or EDI points to bin ls. So we see this is an address because it's a character pointer, right? And a pointer is just a memory address. We can see the arrow showing that it's being dereferenced, and this is bin ls. And then if you're not sure, this is the actual hex representation of these characters. This isn't really necessary, but we could grab this and come over here, open up a new pane, do RAX2, tech big S, and then throw in that. Or I always get this mixed up. Let's do a little s. We can see it prints bin ls and reverse rev. There we go. Just so we're all on the same page and we know exactly what's being passed on the stack and what's getting loaded in all these registers. So bin ls is being passed to system. So now if I continue on, we should see everything being listed. C, continue. So we should see, okay, so this actually errored out with a seg fault, probably because we didn't give it anywhere to return back to safely. But we should have seen the contents of our current working directory printed out. Let's open this back up in Vim. No idea what that is. Vim exploit. Let's uncomment this. There we go. So now when we run the exploit, we see it starts up and it does an actual ls of what's in my current working directory. So that is awesome. We were able to redirect the program execution to go from the normal route it was taking to the useful function address. So what do we need to do now? We want it to call bincat flag.txt, and we saw that string before, right? If I do a robin2 tag z to look at the strings, we see this address is loaded here. Perfect. So just like, where is it at? So just like this has an address for bin ls, right? This is the address for bin ls. We need the address for bincat flag.txt, and we need to take that address and load it into the register RDI. RDI or EDI, they're both the same. EDI is a lower 32-bit portion address range, and then RDI is the full 64-bit register. So how can we do this? This is where return-oriented programming shines. You're going to use something called a ROP gadget. We need to find somewhere in the binary where there is a pop instruction, pop RDI. So if I still have this terminal pulled up, I don't think I still have that debugging terminal. So our data is going to be passed to the stack, and we want to pop, we want to push the address of bincat on the stack and then pop it and save it into the RDI or EDI instruction. So we need to find an instruction we need to find the memory address for the pop RDI instruction somewhere in our binary. And they do have the tools listed here. We can see ROPR or ROP gadget, but for this demo, I'll be using Pwn Tools, and Pwn Tools has a great library called ROP. So we can just load the ELF file. In this example, they have bin.sh, but we'll be using split because that's the ELF that we're targeting. And we can just make a ROP object around that and then just give it what register we would like to find. And it will automatically extract the pop register name and then a return instruction. So if that doesn't make any sense, hopefully it will soon after we showcase what's going on. So I'm gonna open up a Python terminal or interpreter. Let's make sure this is nice and big. Say from pwn import all. Elf will be split. Okay, so once you create an ELF object using Pwn Tools, it automatically runs basically the security checks on it, much like the checksec command that we use sometimes. So it's saying partial relocation read only, there is no stack canary, which is great, NX is enabled, and there's no ASLR, there's no position independent executable in this function, in this binary. Now we need to make a ROP gadget out of it. So let's wrap this to ROP. It takes a little bit to load up. But now if I do ROP, we can see exactly what it is. ROP contains the ELF split, which is what we're analyzing. So we can simply do ROP.RDI, and it prints out the address of this instruction, of this like sequence, right? So pop RDI and then return. So whatever is currently on the stack, take it off the stack, set it to the register RDI, and then return. So this is the address that we want to use. So we can grab this and go back to GDB. And if we want to confirm, let's do examine two instructions from this address. And we can see where we are. We're in libc_csu init. And that's where it found this address or the instruction for pop RDI and return. So this is the correct address. So let's go over to our exploit. And let's make some comments. So here's what we want our stack to look like. We want it to be our buffer, which is 32 bytes. Then we want it to be our base pointer, RBP. And we know this is 8 bytes in length because this is x64. And next we have the return address. This is what RIP points to. That is also 8 bytes long. And I believe here's where we need our ROP gadget. So the pop RDI. And this is at this address. So what is it going to pop from the stack? It needs to pop, the string, right? Robin2 split. I feel like I keep running this. We want to pop this address off the stack because that's the address that points to bincat flag.txt. So first argument, or just argument, first arg. And then from there, we need the ret adder, and then we also need the call system. And we have those addresses notated here. So maybe, right? 40 bytes off the buffer. The return address is 8 bytes long. This is where we'll put the ROP gadget. Pop RDI. And then ret. And then we put the first argument. I know this is just getting uglier and uglier. Oh my goodness. Bincat flag.txt. the return address. Let me say ensure 16-byte stack alignment. And then we'll finally call system. So it should look like system bin cat flag.txt. So that's the goal. That's what we want to do. Let's see if that actually works. Specify that I want this to run in the GDB debugger. Let's add the address of bin cat p64 of this address. What else do we need? We need the ROP gadget. I'll call it pop RDI p64 just to make sure it works for this address. Payload plus equals pop RDI. Payload equals bin cat. So this looks a little bit ugly. But let's save and exit, and now let's rerun it. Python exploit. So this should open it up inside GDB. Let's make sure everyone can read this. We need to set a breakpoint. Where's the address of the read function? Since it's not compiled with ASLR, it will be the same address every time. So let's break here. Let's run the program. We hit our breakpoint. So we see once again, the stack is all zeros. Nothing has been read in as of yet. So if I do an NI to step forward one instruction, we see our 40 A's being thrown onto the stack. We see the address of pop RDI, and then we see the value to bin cat flag.txt is right after it. So if everything goes well, this address, this pointer should be pushed inside of RDI. So let's continue forward with the NI instruction to step forward by 1. And this is nice because it prints out what's currently about to be executed. So let's just NI. Let's step out of this. Okay, awesome. So we see pop RDI is about to be called next. We see bin cat flag.txt is the next value on the stack. So if I do is it just IR $RDI? Yeah, if I just look at the contents of RDI, we see that they point to this. If I examine string $RDI, it's empty. So let's step forward one instruction. Let's execute the actual gadget, the actual pop RDI. So if I do NI, so the pop RDI happened. If I scroll up here, we can see RDI now has this address that points to bin cat. Do NI to return. We're inside useful function. One more. Okay, now we're inside useful function, and we can see the prologue being created. Let's move that to the top. So here's where we are. We can see this little arrow. So we are stepping through this. Actually, this won't work. Because if we look at RDI right now, it has the address we want, right? But if we call this on this line, it'll move bin cat ls into RDI. Ooh, this won't work as expected. NI. Right, because now if we look at it, our argument contains bin ls. Yeah, that's not what we want. That's no bueno. NI. Okay, I know what we can do. So if I run this regularly, not vim, let's change this to run outside of the debugger. Right, it still calls bin ls. So we got it to work. We got the ROP gadget to successfully take the address of bin cat flag.txt and store it in RDI. Remember, for x64, the calling convention dictates that the first argument for a function will be put inside RDI, the second in RSI, then RDX, and so on and so forth. For 32-bit functions, x86 and whatnot, their stack frame, all the functions will be pushed onto the stack, which is different. So what do we need to do? If we open up our exploits, right now, when we're calling system, we're not calling system here because our address is the beginning address of useful function. We instead of having this useful function address, we should have the address of system. So let's go to our debugger, disassemble. We can do this a few ways. We can just grab this address here, 400560, which is the address of system, or we can grab this address inside of useful function. And we can also, if we go here and we do robin2 tag I on split, we see system has this address, which is the same. So let's just grab it from here. Let's grab the address of system from the procedural linkage table. So the address inside libc. So I'm going to delete this. I'm going to call this system. And slap in this address. And instead of having this be useful function, change that to system. So everything should work exactly the same. There we go. So now RDI actually has the register. RDI actually has the value of bin cat flag.txt. It doesn't have, it doesn't get overwritten. So hopefully that made sense. If we really wanted, we could step through it in the debugger one more time, but I think you guys get the points. I could probably clean up this code a little bit. It does look a little ugly, but essentially for return-oriented programming, you would only do this when the stack is marked as NX or DEP, when you can't read or write, when you can't execute code from the stack, right? So if we come here and do vmap, we can see our stack is marked read and write, but we can't actually execute data. So we fill our buffer and we overwrite the base pointer with junk. This could be anything. I just like using A's because it's the first letter in the alphabet. And then we add our ROP gadgets. So we have the return address point to something that we can control or something that we find advantageous. In this case, we did the address of pop RDI because RDI is the first argument for a function call on x64. So we pop something that's on the top of the stack. So what comes after this instruction, what will be on the top of the stack when this is called? OX601060, which is just an address. You can use address and pointer pretty much interchangeably. So it takes the address of this string, bin cat flag.txt, is now stored in RDI. And since RDI is set up, it's good to go. We can finally call system. Before we can call system, we need to make sure the stack is 16-byte aligned, and you can do that a few ways. The way we did it here is by calling, inserting the address of a return instruction, and then we can finally call system. So hopefully that made sense, and hopefully this code is like clean and pretty and easy to follow along at home for you guys. So that's really it for this video. That's how we solved split. Alternatively, we could have used ROP gadget or ROPper. I'll probably showcase that in future videos. But that's really it for this video, guys. Let me know in the comments down below if you found a different way to solve it or anything better. As always, take it easy and see you guys in the next video.